All right, so periodic properties of the elements. um, so when they first put the periodic table together, Mendeleev and a man named Meyer, these scientists, grouped the periodic table to how they kind of thought it was supposed to be. And again, you can kind of see this is discover what their elements as they discover them. But really, Mendeleev arranged them by mass. Okay, they didn't know at the time about protons, neutrons, or electrons. So originally they started arranging it by mass, which worked pretty well, but then Rutherford discovered the nucleus. And then they started rearranging the periodic table by the number of protons because protons determine the identity of the elements. And so if you notice, and when you look across your periodic table, it does go by atomic number 1, 2, 3, and so forth. And it does generally go by increasing atomic mass, but that's not perfect. You'll see if you look around that there are some exceptions. So again, the periodic table is done by atomic number at this point. So periodicity is going to be a patterns that we're going to watch across a periodic table or down a group for a family. And we're just going to pay attention to them and learn about them. And it's going to be these different we call them trends. And then we're going to first start with atomic radius. So that's the size of the atom, how big the atom is. So in math, the atomic radius is determined by the center of the circle, right? So you have your circle in math, not atomic radius, but just the radius. So you have a circle, right? And then you have the center, and out to the farthest line of the circle is your radius. Well, the same thing is going to be true for an atom, but the center of our circle is a nucleus, and this ring right here is going to be our outermost electrons, wherever you're finding valence or outermost electrons, okay? Now, as you go from left to right on the periodic table, the radius across a period gets smaller and smaller and smaller. So we're going to try to understand why. Now, this is in general, okay? And then as you go down a group or a family, the radius actually gets bigger and bigger and bigger. And so again, we're going to talk about why. So terminology that you're going to learn and use very frequently in this chapter is called effective nuclear charge. An effective nuclear charge depends on how many protons are in a nucleus and how many electrons surround the nucleus, how many rings or shells of electrons. So I'm going to use the word ring and shell interchangeably, and you'll see more what that is in a minute, okay? So let's talk about what that means. So the effective nuclear charge, which Zeph, okay, is the charge of the nucleus, that's Z, minus the screening or sometimes often referred to as shielding, all right? And as you go across a period, now remember a period is left to right on a periodic table, the nuclear charge, effective nuclear charge, gets bigger and bigger and bigger, and we'll talk about what that means. And as you go down a group, the effective nuclear charge actually gets smaller. So let's talk about this. We have four different period 2 elements. So if you go on your periodic table, you'll see lithium, beryllium, boron, carbon. I just gave you 4 of them, not all of them, just 4, okay? So they are on what's called the second energy level or second row, if you want to do that. And this second row is often referred to as N. This means principal quantum number or energy level equals 2 because they're in the second row, which means they have 2 rings of electrons or 2 shells. So lithium has 3 protons, beryllium has 4 protons, boron has 5 protons, carbon has 6. And as long as they're neutral, beryllium has 3 electrons, lithium has 3 electrons, beryllium has 4 electrons, boron has 5 electrons, and carbon has 6 electrons, right? If they're neutral, they should have the same number of protons as electrons, okay? So what happens is as you move across the period, left to right, you have the same number of shells. Shells, by shells, I mean rings. This guy has 2 rings. This guy has 2 rings of electrons, or 2 shells of electrons. So we're maintaining the same number of shells of electrons. This guy has 2, this guy has 2, okay? The difference is that this guy has 3 protons in its nucleus, and this guy has 4, and this guy has 5, and this guy has 6, and so forth across a period. We're increasing Z, or number of protons, the charge, right? Protons are positively charged. So the more protons you get, the more positive charge you have in the nucleus. So think of this like a magnet, where you have 2 magnets that are attracted to each other, right? Because we know protons and electrons are attracted to each other because positive and negative attract. So this is like a carbon compared to lithium. This is like a stronger magnet in the nucleus because it has 6 positive charges as opposed to like 3. So guess what it's going to do? It's going to more heavily attract the valence electrons. Now everybody stop looking at the PowerPoint and look at the screen of me, because I'm going to use my hands to kind of demonstrate. Okay, so you have your nucleus, right? And this is your positive charge right here. And then you have your electrons that are around the nucleus, they're just like all kind of floating around in these what are called orbitals around the nucleus. So the stronger this magnet is in the middle, the more attracted the electrons are to it. Well, if electrons are attracted to the nucleus, how do they move? Well, they'll move towards the nucleus. So if they're moving towards the nucleus, that causes the size, or the radius, to get smaller. So that's why the radius shrinks as you go from left to right across a period on the periodic table, because the nucleus and the valence electrons form a greater attraction, which makes the electrons move closer to the nucleus, thus shrinking the atom. So let me see. Yes, I am recording this. I try to record every time. Okay, now here's another trend. As you go down a group, the atom gets bigger and bigger and bigger. Now visually, this is kind of easy to see, right? Hydrogen, what energy level is it on? So you see it, it's right here. It's on this first row right here, right? First row. So it's N equals 1. That means it has 1 ring of electrons. N equals 1. Lithium is on energy level 2. N equals 2. Sodium is on energy level 3. N equals 3. So again, 1 ring of electrons, 2 rings of electrons, 3 rings or shells of electrons. Now I'm going to fill in the electrons real quick. So sodium, we said, or I'm sorry, hydrogen has, if it has 1 proton, it has 1 electron. So this is 1. Lithium is atomic number 3. Sodium is atomic number 11. So 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and so now we're going down. This is our alkali metal family. Obviously, I know hydrogen's not an alkali metal, but it's in the same family because they have the same number of valence electrons. So hydrogen, we say, okay, 1 proton, valence shell is 1 electron. And then we go down and down and down. Now, what I'm about to teach you kind of contradicts what I just told you. Sodium has the most protons in its nucleus. It has the biggest charge of the nucleus. Okay, the nucleus. Remember, Zeph is this. So it has the biggest charge. It has the most protons. And I just told you that the more protons you have, the stronger they pull on the electron and shrink the atom, which is true as you maintain the same number of rings, like when you go left to right. However, when you go down, you are gaining more and more shells of electrons. This guy has 1 shell, this guy has 2 shells, this guy has 3 shells. So the issue is in sodium, while yes, it has more protons in the nucleus, this positively charged nucleus is shielded or screened by these inner shell electrons. What that means is they get in the way of being able to attract this valence electron in the outermost shell. So while yes, you have more positive charge in the nucleus, you also have a greater amount of screening. And so that interferes with the ability of the nucleus to attract these valence electrons. So that's why as you move down a family, the atom gets bigger and bigger and bigger because of all of this shielding or screening that goes on from the inner shell electrons. Okay, so notes are always on the home page of Canvas by topic. All right, so again, as you go down a family, like the alkali metal family or alkaline earth metal family, the atom gets bigger and bigger and bigger, and that's because of the more shielding of the nucleus from the inner shell electrons. This is often referred to, this force of attraction between the positive protons and the negative electrons is often referred to as a Coulombic force. Coulomb's law we'll learn a little bit later. It's a general science term. It's not specific to chemistry necessarily. It's just the force of attraction between two objects depends on their charge and how close or far away they are from one another. Okay, so think of it like magnets. You hold two magnets that would generally stick together if they were close. But if you hold them far apart, they don't really recognize each other, so there's not as great of a force of attraction between the two. Okay, so again, this is just a generic kind of size. As you move across a period, the radius shrinks because we maintain the same number of shells of electrons. However, we increase the charge of the nucleus. So there's no shielding necessarily going on. You'll find out there's a little bit of an exception to this. There's no shielding generally going on because we're all on the second energy level, but we are gaining charge of the nucleus, which makes the electrons more attracted to the nucleus. So as you go from left to right, the radius decreases. Now, as you go from top to bottom, yes, your nucleus gets more and more protons, but it also gets more and more shells of electrons. Those shells shield or screen the nucleus from being able to attract those valence electrons, and so it's not able to pull in as tightly. So as you gain more shells of electrons, the atom gets larger and larger and larger. Okay, this is just an example or a periodic table that has actual values. These values are in picometers. They're actual radii that have been measured. So look, my second period, lithium to neon. Lithium is the largest atom, neon is the smallest atom in that period. Yes, there are always exceptions. I'm not really worried about those at this point. And then look at your alkali metals and then plus hydrogen. This is the smallest. More and more shells of electrons get bigger and bigger and bigger and bigger. Okay, look at helium. More and more shells of electrons get bigger and bigger and bigger and bigger and bigger. All right. So is the reason that the protons attract the electrons toward them and not the nucleus being attracted to the protons? They're technically both attracted to each other, but yes, the nucleus is what contains the mass. It has the protons and the neutrons, and electrons are considered to have negligible mass, so it pulls the protons or the electrons towards the more massive nucleus. That's a great question. Okay. All right, so again, this is the summary. I'm not going to read this to you. This is everything I just said, but we are going to practice. So we're going to rank these or pick which atom is bigger. So I'm going to do the first one with you, and then I'd like you to do the second one, all the rest of them on your own. So magnesium and strontium. So I'm going to go on my periodic table, and I'm going to find magnesium. It's right here. And then I'm going to find strontium, and it's down here. So who is bigger? Well, pretty apparently it's going to be strontium, right? It has more shells of electrons, so its nucleus experiences a greater shielding, thus making the atom larger. So strontium is larger of the two. All right, keep going. So this should be what your final answers are. Between strontium and tin, these guys are both in the same period, which means they have the same number of shells or rings of electrons. This guy doesn't have as strong of an effective nuclear charge because it has less protons. That makes it larger. Any questions before I move on? All right. Size of ions. So ions are things that have charge. So we're going to take neutral parent atoms and then we're going to remove or add electrons to them. Now, there's going to be two things that ionic size depends on. That is what you're doing with the electrons, the number of electrons and where they're going. And then also the number of protons, the nuclear charge still also can play a role. Okay? So here we go. Cations, so those are your positively charged ions, are smaller than their parent atoms. And their parent atom just means the atom, the neutral atom of the same element. So I'll give you the example. Look at sodium. Here's neutral parent sodium. Its cation, Na+, is smaller. So Na+ is smaller than its parent sodium atom. Okay, and we're going to talk about why in a minute. Now, anions you can see, and I'll use, I'll use Cl. Look at chlorine. Here's neutral chlorine, parent chlorine. Look at its anion. Anions of the parent atom are larger. Gaining electrons makes the atom turn into a larger ion. So let's discuss why this is. So I have lithium, and we're just going to use neutral lithium for at first. Remember, this is the first energy level, and this is the second energy level. There's two rings because it's on the second row of the periodic table. So lithium has 3 electrons when it's neutral. So I'm drawing all neutral lithium right now. Has 3 protons in the nucleus and 3 electrons around the nucleus. Okay? Now, again, the radius is just defined as the nucleus to wherever you're finding outermost electrons. Okay? Valence shell, outermost electrons. So I'm going to leave this as neutral lithium. This is neutral parent atom lithium. And now for +1, what does that mean? That means I'm going to remove 1 electron, and we're always going to remove from the valence shell first. So that's like this guy is gone. Well, now I no longer have electrons in my valence shell. I've lost this shell of electrons. There's nothing out there anymore. So I have to change my radius. The electrons are now located here, making the cation smaller radius than its parent atom. Okay, now anions are a little bit harder to look at. So I have this lithium atom, right? And an anion means I'm going to add an extra electron. And then again, we'll always add to the valence shell first. So the problem is electrons repel other electrons. So like if I take and I add an electron out here, this guy right here is like, ugh, get away from me. I don't like you. Oops. And so they will spread out away from each other because they don't like each other. So instead of saying, so now here's the deal. They don't create a new ring. All they do is they expand where the ring is. Okay, so I can't do this, but my shell, I don't create like a new, let me see if I can do this better. I don't create like a new shell. I'm still n equals 2. I just expand now. Whoa. My radius. They just move further away from the nucleus because these guys repel each other. They don't want to be next to each other. You've added an extra electron, and this electron repel, which causes the anion to expand from its parent atom. So an anion is always going to be bigger than its parent atom. Okay? So look at this. These are just examples. Cationic, meaning we're being positively charged. So look at, you have normal potassium. It's 227 picometers. That's its radius. If potassium loses 1 electron, it loses its whole valence shell. So now we only have 3 shells of electrons. Okay, so it's smaller and its radius shrinks. Same with strontium. It loses its shell, its radius shrinks. Now, anions are the opposite. You have neutral chlorine. Okay, and then you add an extra electron. Well, the repulsion between the valence electrons now is huge, and so they spread out. Look, it almost doubles in size. That's how much the electrons repel each other. That's how far away they want to be from each other. They don't even want to be next to each other. Okay, and look at this is oxygen gaining 2 electrons, and its radius pretty much doubles in size. The anionic radius is double its parent atom. Okay, so oops. I would like you to do A, B, C, and D. We're going to wait on E. I would like you to rank them of which atom or ion is larger. Who has the biggest or bigger radius between these pairs? So I'm going to give you a second to do this. So let's talk about these ions right here. I'm just going to use D as an example. Or actually, I'll use C as an example. Calcium ion and barium ion. So you go on here and you go, okay, calcium is right here and barium is right here. Now, +2 means calcium is going to lose 2 electrons to become, remember this word, isoelectronic with argon. And then when barium loses 2, it's isoelectronic with xenon. Obviously, this means the barium ion would have 5 rings of electrons now, while the calcium ion would only have 3. So obviously, the barium ion is larger. Okay, so let's remember that terminology of isoelectronic. Okay, now these two guys, sodium ion and aluminum ion. What do you recognize about them? So here's sodium, here's aluminum. When sodium loses 1 electron, it becomes isoelectronic with neon. When aluminum loses 1, 2, 3 electrons, it becomes isoelectronic with neon. So this sodium +1 cation and this aluminum +3 cation are isoelectronic with each other. So this isn't a trick question, but I'd like you to draw with me. Okay, so I'm going to do my best. So I'm going to do neutral sodium first. It's on the 3rd energy level, so it has 3 rings of electrons. Then I'm going to do aluminum. Okay. Neutral sodium has 11 electrons. Neutral aluminum has 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so this is aluminum. Oops, I'm sorry. This is sodium, neutral sodium, and this is neutral aluminum. Okay, now these say on our notes, this is supposed to be sodium +1. Well, what does +1 mean? Well, +1 means I'm going to remove 1 electron, right? So I get rid of my valence electron, and now I no longer have electrons in this outermost shell. So this is sodium +1. Okay, aluminum +3 is going to mean I'm going to get rid of 1, 2, 3 valence electrons, and now I also no longer have electrons out here anymore. And you go, uh-oh, they have the same exact number of electrons. They both have 2 rings of electrons now. They both lost their outer shell. They both have 2 rings of electrons. And so one would think, oops, this is aluminum 3+ now. So a common misconception is to think that they have the same radius. That is incorrect. They do not have the same radius. They do, however, have the same number of electrons. They have the same number of electrons. They have the same number, same number of shells. of electrons. So what do you suppose matter? Good job, Martin. More protons. This guy has 13 protons, right? We don't mess with protons. This guy has 11. 11 protons is less nuclear charge, therefore making it bigger. Okay, so sodium ion is bigger. Ooh. So when the two elements are isoelectronic, it's the number of protons that play the role, also known as the nuclear charge, because that's the charge of the nucleus with the protons in there. I had a question that asked, how do I know how many electrons go on each ring? And you don't need to know that yet. You will when we do our next chapter. 2 go on the first ring, 8 can go on the second ring, 18 can go on the third ring. It's a pattern, and we'll talk a lot about it more second semester. All right. So look at these guys. Arrange these isoelectronic ions in order of decreasing size. So what does that mean? That means decreasing. Largest radius to smallest radius. Now, if you notice that all 4 of these ions are isoelectronic with one another, all 4 of them. So and who are they all isoelectronic with? So when potassium loses 1, it's isoelectronic with argon. When calcium loses 2, it's isoelectronic with argon. When sulfur gains 2, it's isoelectronic with argon. When chlorine gains 1, it's isoelectronic with argon. Meaning all these guys have the same exact number of shells of electrons. They all have 3 shells, right? Because when potassium loses 1, it's now on the 3rd energy level. It loses its valence shell. And then the same when calcium loses 2. So let's rank them. If they have the same number of electrons and the same shells of electrons, it's going to be protons that play the role. So potassium has 19 protons, calcium has 20, chlorine has 17, and sulfur has 16. So who is the biggest?
Calcium. No, sulfur.
The sulfide ion, because they all have 3 rings of electrons now that potassium and calcium have lost their electrons. These were originally on the 4th energy level, yes, when they were neutral, but not after they lost their electrons. They lose that outer shell. So the largest radius is this sulfide ion, because it has 16 protons in its nucleus. That's the smallest. That's the least effective nuclear charge here. So then it's chloride, which has 17, and then it's potassium, which has 19, and then calcium has the highest effective nuclear charge of the 4. More protons, stronger pull towards the nucleus. Any questions? Okay. So that was atomic and ionic radius. So now we're going to do ionization energy. So ionization energy is the amount of energy required to remove an electron. So we're trying to remove electrons. Okay. Now, the reason why it's called ionization energy is because when you remove an electron, you create an ion. Specifically, you create a cation. Getting rid of negative makes you more positive. So what you have to do for this, and this is where kids really struggle, is remembering what it means to remove an electron. If something has high ionization energy, that means it's difficult to remove an electron. And the electrons that are closest to the nucleus are the most difficult to remove. Okay? So there are what are called successive ionization energies. And that means like your first ionization energy is the amount of energy required to remove one electron. So they take sodium, they turn it into a gas in this really crazy container that heats it up super hot. They put in energy, usually they shoot some sort of radiation at it. We'll talk about this later, okay? And what that does is if it's high enough energy, you can rip off an electron from the sodium. Now, if you rip an electron off of sodium, you create sodium plus 1 cation. And then you could take this cation and keep putting in energy, okay, to try to rip a second electron off. That's why this is called second ionization energy. And if you rip another electron off, you become plus 2, and so forth, and so forth, and so forth, okay? So as you go across a period, left to right, that means left to right on the periodic table, left to right on the periodic table, ionization energy tends to increase. Why? It becomes significantly harder to remove electrons that are closer to the nucleus. Why? The closer they are to the nucleus, the more strongly they're held by the nucleus. If they're held strongly by the nucleus, they don't want to let you rip them off, so they will have higher ionization energies. It will be harder to rip them off. Okay, now as you go down a group or a family, the atom gets bigger and bigger and bigger and bigger, meaning those valence electrons are getting further and further and further away from the nucleus. So those valence electrons experience more shielding, meaning the nucleus doesn't attract them as strongly, so they're easier to remove. So ionization energy decreases as you go down the table because it becomes easier to remove them the bigger the atom gets. Oops. So if you look on this table, these are actual ionization energies that were determined experimentally. I'll look at period 2. As you go across here, your atoms get smaller and smaller and smaller, and your ionization energies get bigger and bigger and bigger. They become more and more difficult to remove electrons that are starting to get closer and closer to the nucleus. Okay? Now, if you go down a group, the atom gets, I guess I should have done this on the side. The atom is smallest. We'll talk about hydrogen later. I know this is an exception, but in general, as you go down the group, the ionization energies get smaller and smaller and smaller. So the smaller they get, the more easier they are to remove an electron. Now, this is what determines reactivity as well. So the easier it is to remove an electron, the more reactive an element is. The harder it is to remove an electron, the less reactive an element is. So look at this conceptually. Oops. Which family has the highest ionization energies on this periodic table? Noble gases. Now this should make sense. What do you know about noble gases? They're super duper duper unreactive. Why? Well, they're the smallest in their period, okay? But they also have full valence shells of electrons, right? They have what are called an octet of electrons. And again, we'll go more into this on Friday. Meaning they don't want to let you take an electron. They're stable. They want to be left alone. So if you try to yank an electron off of them, you're going to have to put in a lot of energy to do it, okay? So high ionization energies, low ionization energies over here. Your alkali metals are like, they have one valence electron. They're like, ugh, I don't care. I don't want this electron. Please take it. So it doesn't take a lot of energy to try to rip electrons off of your alkali metals. Okay. So let's rank them. Which of the following pairs, or for each of the following pairs, predict which has the highest first ionization energy. So when they say first, it's just to remove one electron, the first electron. And again, we're always going to remove from the outermost shell first. That's where you would always start because they're the furthest away from the nucleus. So magnesium or sodium, who has the higher first ionization energy? So when you see this, higher first ionization energy, you need to think harder, more energy to remove. So let's do magnesium and sodium together. So you find magnesium and you find sodium. So here's magnesium, here's sodium. Who has the higher first ionization energy? And the answer is magnesium. And why is it magnesium? Magnesium is smaller than sodium, so its electrons are closer to the nucleus, which means they experience a greater force of attraction to the nucleus and therefore would be harder to remove. Okay, you try the rest. These are the answers we should have gotten. Does anyone have any questions on how to determine who has a higher or lower first ionization energy? For E, okay, let me double check my periodic table. Someone asked for E. So Na and aluminum are in the same period, which means they have the same number of shells of electrons, but aluminum has is smaller. It has a higher effective nuclear charge because it has more protons in the nucleus. So that means its electrons are closer to the nucleus, making them more difficult to remove. Does that help? Okay. So now, all right, we're only going to do part C of this. And then I'm going to do the first one with you. This is a sample FRQ from 2000. And when they give you periodic trends and ask you to explain them, they are very, very picky about how you answer them. Meaning if you don't answer them in a way that shows that you actually understand what you're talking about and you just spit out definitions, that you won't get any credit for it. So I'll do the first one with you and kind of show you what is expected of you. And like what won't work, and then I want you to try the second part of part C. So we'll skip part B for now. Let's see. So in terms of atomic structure, explain why the first ionization energy of selenium, and then the first part says, is less than that of bromine. So we find selenium and we find bromine. So let me get rid of all these. Selenium and bromine are right next to each other on the periodic table. So here's selenium, here's bromine, and it says that selenium has a lower ionization energy relative to bromine, and you need to explain why. So I'm going to give you what a standard explanation could be. Now here's what it can't be. You can't say selenium is bigger, so it has a lower ionization energy. That is a horrible explanation. You're not wrong, but you don't understand. So what that it's bigger? What does that have anything to do with ionization energy? You have to thoroughly explain it. So selenium is larger. Did I say smaller? Selenium is larger than bromine. Okay, it has a weaker effective nuclear charge. So because it's larger, its electrons are further away from the nucleus. Because its electrons are further away from the nucleus, it has a lower ionization energy because it's easier to remove those electrons because they don't experience as strong of a force of attraction as bromine does. You need all of that in some sort of words. It can be rearranged and such, but you need all of that explanation to get full credit. You can't just be like, oh, it's bigger, so it's easier to remove. Like, you've got to explain why is it bigger, what does that have to do with ionization energy, and so forth. So having said that, I would like you to see if you can do the second part and try to write out your own explanation of why selenium is has a greater ionization energy than tellurium. So now you go over here and you go, okay, well, where's tellurium? Okay. So now this time, selenium has a higher ionization energy relative to tellurium. So take a second and I want you to see if you can write down a beautiful explanation for this that you would get full credit on the AP test. You should say for selenium having a higher ionization energy than tellurium, something to the effect of selenium has a smaller atomic radius. It only has 4 shells of electrons while tellurium has 5. So its electrons experience a greater attraction, or sometimes referred to as Coulombic force, to the nucleus, and because they're close to the nucleus, they are held more tightly, which makes them harder to remove, thus giving them a higher ionization energy. It is more difficult to remove electrons that are closer to the nucleus. Something like that. Any questions? Okay, so this is where I have to start skipping a few things. All right. So I skipped those 2 slides. We're going to go to here. Successive ionization energies are just, ripping one electron off, then ripping another one, and then another one, and then another one, and then another one. They just call them successive ionization energies. So now, really quick, we're going to kind of do a review. It seems we're a little dusty on like how many valence electrons everything has. You guys needed to know that in order to write chemical formulas, because you needed to know how many things everything wanted to gain. So let's do valence electrons. This family has 1, this family has 2, this family has 3, 4, 5, 6, 7, and then 8. This guy only has 2, but the rest of these are 8 from here on, okay? Now, because of the valence electrons, it also determines what sort of ion they want to become, right? So, let's see. So this is 1 valence electron, so they want to lose 1, so they become +1. Want to lose 2, +2. Want to lose 3 electrons, +3. This group is plus or minus 4. Now, we're working on, we can either lose 5 right here, or we can gain 3. So then it goes -3, -2, -1, and then no charge here. So these again are common ions. Common ions are in this color. All right. So let's look at the this thing right here. So sodium has 1 valence electron, magnesium has 2, aluminum has 3, silicon has 4, 5, 6, 7, 8. So let's look at the successive ionization energies. What this means is that if you look at sodium, this is the amount of energy required. So sodium plus 496 kilojoules per mole of energy to rip an electron off of it. That's what ionization energy is, removing an electron. So this is how much energy you have to put in to get rid of an electron. Now, what do you know about sodium? After sodium loses its 1 valence electron, I'll redraw again. Okay, so here's neutral sodium. It loses 1. So that means there's nothing in the outer shell anymore. So now, when it loses the 1 electron, its radius gets smaller. Is that right? Its radius gets smaller. And it also has a full valence shell of electrons. So what this is showing is this is showing a jump. We call it a jump between the first and second ionization energies. So it's like it didn't take a lot to rip off the first electron, but there's a huge jump if you want to try to take another electron. It has a full shell of valence electrons. It's changed its size, so it doesn't want to give you a second electron. So we say that there's a jump between the first and second ionization energies, meaning it's like it's okay losing 1, but it doesn't want to give you a second one. All right? So what does that say about magnesium? Well, magnesium you put in energy. Oops. Do it this way. You put in 738 kilojoules per mole of energy, and you get magnesium ion and an electron to rip the first electron off. Now, to do it again, you would have to take the magnesium ion and add 1,450 kilojoules per mole of energy to rip off a second electron. So that would be Mg now 2+, and then another electron comes out. First electron, second electron. Now, this is 738, and then it was like another 700 to rip off the second one. And then look at this jump right here. It's now 6,000 to do another one. This is considered a jump. This is quite a difference between the second and the third ionization energies. Well, why? Well, after magnesium loses 2 electrons, it loses its outermost shell of electrons. It becomes isoelectronic with neon, meaning it's smaller, it has a full valence shell, it doesn't want to give you any more electrons. I mean, you can, but you're going to have to pay the price and put a ton of energy in it. So magnesium experiences a jump on the removal of the third electron. So the jump is between the second and the third ionization energies. Now, I do want to go over something real quick. Why is it harder to remove the second electron from magnesium than it was the first one? Does anybody know? Okay, so you go, okay, you rip off one. Now that's the first ionization energy. Oops. Why do you think it's harder to take another one? Now it's not super hard. Magnesium's like, okay, I'll still give you another one, but you are gonna have to work a little harder for it. Why? So this is a concept we've learned. Good job, Micah. Less electrons out here means there's less repulsion between the electrons. So this guy's actually held a little bit more tightly because there's less shielding or less repulsion. So that repulsion causes this electron to be held slightly a bit more tightly. So it takes a little bit more work to pull it out. Not a ton, but a little bit more work. Okay, and then look at aluminum. Aluminum has 3 valence electrons. So it's like, okay, I'll give you one, I'll give you another, I'll give you another, and then it jumps up to 11,600 if you try to take a 4th electron from it, okay? So these questions, for which electron will the ionization energy jump significantly for strontium? So you go to your periodic table, you go, okay, strontium is right here. It has 2 valence electrons, meaning it's like, it's okay losing 2, but it doesn't want to lose a 3rd. So your jump would be with the removal of the 3rd electron. And then it asks you for gallium. Now gallium is a little harder to see, but it's right here, okay? So you can just ignore this. This is 4th energy level. So it'll lose 1, 2, 3. It's okay losing 3, but after it loses 3, it doesn't want to lose any more electrons, so the 4th would have the jump. The removal of the 4th. So which should have the largest difference between first and second ionization energies? So what does this mean? Which one's going to have the biggest jump from the first removal to the second? Meaning it's cool losing the first one, but it doesn't want to give you a second. Who's going to have the biggest jump for that? It's going to be the one that is okay losing 1 and not okay losing 2. So who is that going to be? That's going to be sodium, right? Sodium has 1 valence electron. It'll let you have 1. It is really not going to want to let you have a second. Now, it is true that the removal of a second electron in all these is going to require more energy, but not as much as sodium. Once sodium loses 1, it doesn't want to lose anymore. The rest of them can afford to do that. But sodium does not want to. It loses its shell when it only loses 1, and it's smaller, and it has a full shell after it loses 1, so it does not want to lose anymore. Oops, I keep doing that. All right, so this says, consider the successive ionization energies. How many valence electrons does R most likely have? So pretty much you want to find out where the jump is, how many it's okay giving, and then when it stops giving. So how many valence electrons does this most likely have? Well, like it looks like, okay, this is okay. This doesn't look like too big of a jump. 700, another 700. And then, oh my, it's another. So this was a difference of 700, and this jumped to a difference of 6,000. Look at this. This is a difference of 3,000, 3,000, 3,000. So the biggest jump was here, a 6,000 almost kilojoule jump. So the biggest difference is between the second and the third, which means it's cool giving you the first 2, but it doesn't want to give you a third, so it most likely has 2 valence electrons. That's how many it was okay losing. Well, if something is losing 2 valence electrons, it becomes +2. And I want to write the formula of its oxide. So oxygen's charge is -2. So you should remember this from writing chemical formulas, right? So what would its formula be? It would be RO. I guess I should write that down here. RO. +2 and -2 go together perfectly. So, all right, I'm skipping this. All right, this guy. So we go, okay, based on the information in the table, what would the most likely formula be for the unknown substance with nitrogen? Well, nitrogen's common ion is -3. It would like to gain 3. So this unknown, I need to figure out how many valence electrons it has from these jumps. So it looks like here, this is another 700. Ugh, this is the jump again between the second and the third. So if the jump happens here, this most likely has 2 valence electrons. If it loses 2 valence electrons, it becomes +2. So between a 2 and a 3, the common charge is 6. So you'd need 3 of these and 2 of these. So that's this formula. All right. So speaking of this, let's do A and B. So it says using principles of atomic structure, explain these statements, and you have to include both substances. So A says the atomic radius of lithium is bigger than that of beryllium. So you go to your periodic table, you find lithium, you have beryllium. Okay, they're all in the same, they're both in the same period. So why is lithium bigger than beryllium? Well, I would go on to say, okay, lithium and beryllium both have 2 shells of electrons. They're in the second period. But lithium has 3 protons in its nucleus, while beryllium has 4. And the more protons you have in your nucleus, the more of an effective nuclear charge the nucleus has on the valence electrons, therefore making the atom smaller. So beryllium is smaller than lithium, and lithium is larger. Something like that. Okay. Now, this says the second ionization energy of potassium is greater than the second ionization energy of calcium. So you go, okay, well, here's potassium, here's calcium. Potassium has 1 valence electron, calcium has 2 valence electrons. When potassium loses, so the second ionization energy is the removal of a second electron. So you got to take off 2 electrons. Well, potassium has 1 valence electron. So this is what I would say. Potassium has 1 valence electron and calcium has 2 valence electrons. Once potassium loses 1 valence electron, it loses its outermost shell of electrons and becomes isoelectronic with argon. That makes it smaller, and that makes it more attracted to the nucleus. And because of that, it's not going to want to give you a second electron. Calcium has 2 valence electrons, so it can afford to lose 2 before it loses its valence shell. So potassium will have a way bigger jump if you try to take a second electron from it, or a second ionization energy. Something to that effect. All right, so we are skipping these. Sorry. We will do this once. All right, 2 more things and then I'm done. So periodic trends. So we're doing now electronegativity. Now be careful because we're also going to do something called electron affinity, and they're similar but actually different. So of course it's not plugged in. All right, so electronegativity is an element's ability to attract electrons. So it's the attraction to electrons in a chemical bond. So electrons will spend more time around the substance that is more attracted, or element or whatever, to the electrons. And the smaller an atom gets, the more electronegative it gets, because the electrons can get closer to the nucleus. If electrons can get closer to the nucleus, they will, of that atom, it will experience a greater Coulombic force. So again, electronegativity is attraction to electrons. How attracted an atom is to the electrons within a chemical bond. Okay? So if you don't remember, hold on one second. We had to do this when we did, what was it called? Oxidation states, okay? The three most electronegative elements on the periodic table are fluorine is the most, and then oxygen, and then nitrogen. The closer you are to fluorine, the more electronegative you are, okay? Because the closer you are to fluorine, the smaller you are. Now, we're going to ignore our noble gases in this because we're going to say they don't have any attraction to electrons, right? Their valence shell is full. They are stable. They don't want any more electrons. So we're going to just kind of ignore them in this trend. So again, electronegativity increases as you go this way because the atom gets smaller and smaller and smaller and smaller and smaller. So the electrons can get closer and closer and closer to the nucleus, experiencing a greater attraction. So that means electronegativity decreases this way. Well, why? The atom gets bigger and bigger and bigger and bigger. The electrons are further away from the nucleus. They are shielded by the nucleus, so they can't attract electrons very well. Okay, so, So we're going to rank these by increasing electronegativity. So what does that mean, increasing? Low electronegativity to high electronegativity. Okay, so lowest electronegativity means least attracted. Neon, right? Noble gases aren't attracted to electrons at all. They don't want electrons. They don't want to lose them. They don't want to gain them. They just want to be left alone. Okay, so then go to your periodic table. Who's next? Who has the next lowest attraction? Well, these guys are the biggest, right? They're on the 4th energy level. And potassium is the bigger of the two, right? Between potassium and zinc. So potassium is next, and then zinc, and then chlorine. Again, the closer you get to fluorine, the more electronegative you are. So then it's potassium, zinc, chlorine. Any questions? Okay, so here's a little chart. Again, these are actual electronegativity values. Notice that the noble gases are just not included in this trend, this specific trend. It is only this one where they're not included, okay? And so as you move across and the atom gets smaller and smaller and smaller, the attraction to electrons, electronegativity, gets larger and larger and larger. And as you move down and the atoms gets bigger and bigger and bigger, the attraction to electrons gets smaller and smaller and smaller because the nucleus is shielded by the inner shell electrons. We're completely ignoring lanthanides and actinides right now. Very good question. And we're actually kind of even ignoring our transition metals, which we'll talk a little bit about a little later. Okay, so again, these are just other examples. Again, this is the trend, ignoring the noble gas family, which is why it's scratched out. And this last thing that we're doing is electron affinity. And you go, okay, well, what is the difference between electron affinity? Well, the main difference is the actual energy change associated with something actually gaining an electron, not being attracted to it, actually taking in an electron and becoming negatively charged. So here's an example. You have neutral chlorine. It gains an electron to become the chloride ion. And this much energy is, what does that negative mean? There's no such thing as negative energy, so think back to thermo. Negative energy is this much energy is released. The more energy that's released from an electron affinity concept means that substance, that element, must have really wanted to gain an electron. if you have low electron affinities and not a lot of a lot of energy is released, that means they have low electron affinities, meaning they don't gain electrons very easily. Okay, now it's hard because we look at negatives and we think magnitude, and you go, well, isn't this a low number, like negative 349? Well, the answer is no, because there's no such thing as negative energy. This is a high electron affinity because it is releasing a lot of energy. The more energy something releases when it gains an electron, the more easily it had taken in the electron. Okay, so if you look at these, and there are so many exceptions on here that I don't need you to know yet, okay, let's just focus on our halogen family relative to our alkali metal family. Okay, what do we know about alkali metals? They have one valence electron. Do they want to take in any electrons? No. In fact, they're trying to get rid of electrons. They're not trying to take in electrons. So they have pretty low electron affinities. They do not release, so low electron affinities. They do not release a lot of energy to take in an electron. So they must not really gain electrons easily. Look at your, and I'm ignoring this guy right here. I'm ignoring right now. Look at your halogens. They release a ton of energy when they take in electrons. Look at how much energy is being released here. Why? Well, these guys have 7 valence electrons. They really want one more. All they need is one more to achieve stability. So they release a bunch of energy when they do. That means they take in electrons very easily. Okay? Now, let's look at your noble gases. Your noble gases have positive, greater than 0 means positive electron affinities. What do you know about positive energies or electron affinities? That means you have to add energy. No energy is being released. You're putting in energy. Meaning if you try to make any of your super stable noble gases gain an electron, you got to put energy in. It's not giving off any energy when it gains an electron. You have to force this to happen by putting in energy. So they have extremely low electron affinities. They do not want electrons. Okay, we're going to skip this. So we're going to rank these, and then I'm going to be pretty much done. So rank by increasing electron affinity. So that means low electron affinity. What does this mean? It means little energy released upon the addition of a electron. AKA doesn't want electrons. And then so high electron affinity means a big release in energy. Means this guy really must have wanted an electron. Okay? So who's the lowest? That's going to be neon. Neon has a positive electron affinity, meaning you have to force neon to try to take in an electron. And then who? Oxygen will release a lot more than neon, which means it must gain an electron easier. And then fluorine is the highest of the three. Meaning fluorine takes in an electron the easiest. Easiest addition of an electron. And this is the hardest addition of an electron. Okay. All right. So, having said that, I am done with, except for the slides that I skipped of this chapter. I will come back to those. You need to do this periodic table review. You need to do this periodic table review. From here all the way so this is all just different properties of different elements, and we're going to talk more about this, but I'm not going to teach you this. This is going to be like reading like you would do in any other class. You'll be responsible for it. The only thing I will go over with you are the slides that I skipped, and then so you need to go to here. Metals differ from non-metals. Everything else I will go over with you when we go back and I teach you the other chapter. So this is where you need to review on your own the end.